Hello, this is Mr. Wyrick, and today I'll be talking to you about lesson 12.7, the next to last lesson from chapter 12, and this is about spherical geometry. These are kind of muddy waters. We're just kind of wading in a little bit, show you a little bit about what's going on with this for this lesson to understand more about spheres, and then we're going to kind of move on. I'm going to check the test to see if there's a lot of these questions, because this is going to be some more difficult kind of stuff. It kind of harks back to what we were doing like in some of those early chapters about this is true, this is not true, can you prove it's true? And this kind of throws some of that stuff out the window. What we have studied so far is called Euclidean geometry or plane geometry. So everything is planes, like flat planes, like this top of this desk here, or an imaginary plane where we have the X and Y axis, or three-dimensional space, but we think of it still as squares. When we're talking about spherical geometry has to do with the geometry that you do on the planet's surface, understanding that the floor is not actually a flat plane and over a long distance it's going to curve because the Earth is a sphere. So we're talking about spheres. One of the main differences, and I have an H missing. There we go, spherical geometry. And I missed one up there too, wow. Okay, so spherical geometry, we've got the great circles. If you remember from the last lesson, the great circles are like a diameter. They're going to go around the largest part in any direction, but they're going to contain, if you were to cut it in half, that center would be there where you cut it off. So the smaller circles, anywhere else that you would cut it, if it's not directly in half of that sphere, that is not a great circle. Only the great circles in spherical geometry are counted as lines. This can lead to some different issues. So on page 890, there's some comparisons between plane geometry, Euclidean geometry, and then spherical geometry. And when we're talking about spherical geometry, the first one is through any 2 points, there's going to be one line. When we're talking about a plane, like up here on the board, if I put a point here and I put a point here, there's only going to be one line that could potentially go through those 2 points. But if I'm dealing with this tennis ball here, if I put a point here and I put a point around on the other side where a line could go through them and make a great circle, then there's more than one great circle that could potentially go through both of those points as long as it looped around. So we could go at an angle and still contain those 2 points. We could go at an angle this way, still contain those 2 points. We can go around this way. We can go around this way. There are lots of lines that could go through those 2 points. So this no longer applies, which means it's non-Euclidean geometry. If the postulates fail, if the stuff that's supposed to happen doesn't work anymore, it will still work. We just have to understand we're dealing with spherical geometry and we're no longer dealing with plane geometry. If we have a line, such as this one, and there's one other point, then only one line is going to be parallel. Understanding again that all of our great circles are going to be the lines, and that's the only lines that we have in this type of geometry, in spherical geometry. None of them are going to be parallel. Any other parallel kind of cut that you could make through this to potentially make a line, it would not be a line because it's not a great circle. It doesn't go through where we would have a diameter going across the middle. The last one that they have is the angles of a triangle add up to 180 degrees. Well, again, you have to kind of imagine here, but let's say I've got a line going around this one that's going to go like this. And so I've got another point over here and I've got a point up at the top to where these lines would all go down through here. This is 90 degrees. This is 90 degrees. So with two 90-degree angles, I'm forming a triangle. Now this has an arc. This has curve to it in three-dimensional space if we flatten it back out and try to make a net. But when we're talking about spherical geometry, in this case, these are 90-degree angles, 90-degree angles, and we've got another angle up here at the top. Because we have two 90-degree angles already, we're going to have more than 180 degrees in that triangle. Now, what does this mean for you with this lesson? Basically, you're going to be asking if something is or is not a line according to the spherical geometry terms. You're going to be classifying some stuff and you're going to be doing some work on does it apply, does it not apply with the problems in this one. The spherical geometry, some other kinds of non-Euclidean geometry that you'll take a look at in this one. So the questions are going to be a little more difficult, require some thought. There's not going to be as much math on this lesson, so you do have to kind of be careful about just the way that you're thinking here. For the problems that we're going to work on this one, we'll go 9 through, we'll say 26. 9 through 26, I do want you to capture some of those alternate forms of geometry that they only have in those higher order thinking problems, just so you get kind of a taste, again, of what's coming up. If you start to get into some three-dimensional math later on, where you get outside of the limitations of Euclidean geometry, it could be interesting to look back on that and know that you have seen it before, had a slight introduction. If there's something about this that you don't understand, something you need explained a little bit better, of course, make sure to come in, check with me, come in during tutorial time, or ask during class. I'd love to explain it to the whole class if I need to, and we'll see you then.